engineering department and the Interdisciplinary Institute for Network Science. And this is that better now? Okay. I had problem in the panel before, actually. You're right. So, and that's work we did together with people from Bell Labs, Borst, Anwar Walid, and Mohammed Girsa. It relates, we are from a networking background, so it relates to delay, what Professor Zohar was mentioning yesterday morning and what you mentioned earlier today. And it was presented at Infocom, big networking conference this April. So, in a nutshell, what we did is we developed a stochastic model for proof-of-work blockchains. And we tried to quantify how the growth rate, how many blocks are added over time to the chain, and the wastage rate, or orphaned block rate, how many blocks are orphaned over time, behave as a function of the parameters of the network. And what I mean by parameters of the network, I mean the number of nodes in the network, I mean the computational power of the nodes, the communication delays of the network. So the role of delay in the scalability is something we studied, and also we showed, as other people have showed also, but we did some work on how delay affects the vulnerability of the network. And we will comment on how we can use these results to achieve some design goals if we want to design a network. So the model in a summarized way, we have k nodes in a blockchain network, so we fix the size. As we know from all these days and these discussions, the block generation happens as a Poisson process, very many trials with very low probability, that's a Poisson process. We assume that every node keeps their individual chain, individual branch, the blue ones, and there is a main branch which is the blocks that everybody agrees upon. So this is finalized, this is not going to change, these things change. And we denote by y the length of every branch. The block generation is a Poisson one, so whenever a new block is added, the individual branch increases by 1. What happens when communication happens? Communication, we model it as an exponential distribution according to the Decker and Wattenhofer measurements paper. So there is a parameter mu KL that is for the communication between nodes K and L. What happens when they communicate? They synchronize. So the one with the longer chain wins, the other chain dies. If they have equal length, they continue to compete because they want to collect the reward from the mining. So we will study the dynamics of this model. I will show you first in a 2-node example because it's easier. And the goal is always to express the growth rate as a function of those parameters. So we have 2 nodes with hash powers, lambda 1 and lambda 2, and delay equal to 1 over mu, the exponential distribution parameter. And we have a state diagram here for this Markov chain because all those individual branches lengths form a Markov chain. So 1,3 means that node 1 has 1 block in his individual chain and node 2 has 3 blocks. So what happens when node 1 finds a new block? We transition to the right. Coordinate 1 is increased by 1. Similarly for node 2, the more interesting part is what happens when communication takes place. So if we are in a non-diagonal state, this means that one chain is longer than the other, so we go back to 0. The 2 nodes synchronize. However, if we are in diagonal state, they continue to compete. And that's a problem, because if we want to find the stationary distribution of this process, that's a bit difficult to find it in a closed form as it is. So we did a trick. Because we're interested in the long-term growth rate, it doesn't really matter if these 3 blocks are going to be added to the chain right now or later from a non-diagonal state. So the trick we did is to add the diagonal transitions. And in terms of the growth rate, this is indifferent. So now we can easily find the stationary distribution. And the growth rate is just the average over all states weighted by the probability of each state, the average of the number of blocks added to the chain, which is the max of the 2 lengths of the chains, times the rate with which this happens, which is this mu here. So this is a general formula. It's not directly related to the parameters of the network. How can we do it? We can assume a low delay regime, which is absolutely realistic in Bitcoin. And we can do that in order to get asymptotic expansions for terms of this form. I'm not showing all the details here because of the time constraints. And eventually get a formula for the growth rate gamma as a function of the hash rates and the communication delay, and also the number of nodes, which is in this case is 2. When it gets more interesting is when the nodes are not 2, but are arbitrary in number, so k nodes. The math is a little bit more complicated here, the stochastic analysis, but eventually what we get is two formulas that relate gamma and theta with the parameters. What is a bit interesting here is that the wastage rate is related as k log k with the number of nodes in the network. So as more nodes get into the network, that's the wastage rate we expect. And if the delay is 0, then as we expect, this term is 0. So we take advantage of the whole power of the network, which is k times the individual power. So this can give us some design insights in case you want to create your own network. We did some experimental validation in a test, but we didn't have something in our basement. But we used Genie, which is a cloud platform that gives you VMs around the US, at Stanford, Columbia, and so on. So the delays are somewhat realistic because they are geographically distributed. So I have less than a minute. I will very quickly talk about some simulations we did about delay and security. So we have one attacker and 100 honest nodes. We vary the delay and the attacker's power. And what we want to show here is the probability of successful attack on the vertical axis and increasing number of confirmations here, increasing delay here. And we calculate the probability with 4 different methods. 10 seconds. The blue method is not taking delay into account. It's from Manny Rosenfeld's paper. The others do in different ways. So the takeaway is that the probability of successful attack is by orders of magnitude higher in the presence of delay, which is what we expect and what is ignored many times. So that's the summary. I think that's it. Thank you. And I'll be happy to talk about it. I have a poster downstairs if you want to discuss. Question? Oh, yeah.
Okay, thank you. Hello to the survivors of the day. I'm Attila. I'm a PhD student at the Budapest University of Technology, and I will talk about permission blockchains, namely Hyperledger Fabric. So this is a little bit perhaps closer to distributed computing than public blockchains are. So imagine an evil Spock but only with a 5 o'clock shadow on his face and not a full beard. So what do we get from permission blockchains? First, we get known identities. So does this mean that we can start trusting each other now? Not really, but we can trust the technology that if something goes wrong, we can find out who is responsible. And this auditability across organizations is a really big plus. The other sales pitch is, of course, the increased performance. Since we control the topology of the network, we can design it to be fast. So it sounds easy, right? Well, not really. Although if you pay enough money to someone, then probably this is the abstraction level you will see. We accept bitcoins. So what we model in is the Hyperledger greenhouse, which contains several blockchain platforms, for example, Hyperledger Fabric, and several tools that makes our lives easier, like Hyperledger Caliper, that helps us with the performance measurements of such platforms. Fabric breaks with the traditional approach to order then execute, like we see in Bitcoin and Ethereum, and as we know from active state machine replication, and uses a twisted version of this execute order validate approach. First, the transactions are executed independently of each other, and their effects, and only their effects, are gathered as read-write sets. And this enables the system to scale really well, embarrassingly well, and these read-write sets of the transactions are used to ensure their deterministic results. Then these change proposals are sent to an ordering service, which only sees them as something to order. It globally orders them and then broadcasts them. Since this is a simple stateless service, it's pluggable, and we can decide on what kind of tolerance do we need. Do we need only crash fault tolerance or even Byzantine fault tolerance? As the final stage, the orderer service sends the assembled blocks of transactions back to the standard nodes in the network, and there they do some policy validation and they do some multi-version concurrency check control against their results, which is basically stolen again from the database people, and this is to guard against double spending. And as the last step, which is really a technical step, the results are persisted in the worst state, which is kind of like UTXO cache, and written to some database, LevelDB or CouchDB, which, as we know, doesn't support 1 million transactions per second. We also measure this. So this is the detailed life cycle of the transaction in Fabric. Coupled with the previous explanation, designing for performance actually kind of looks like this. So it's not easy. How we tackle this approach? We basically start here up. We define some use cases, scenarios that has to be representative, otherwise our measurements will be not meaningful. This is actually a lot harder than it sounds, since blockchain is kind of a new trend around here. So where do you get this usage of the platform to emulate? Then, based on these defined scenarios, we configure the system under test, and we use Hyperledger Caliper to perform the actual measurements and workload generation. And after this, the fun begins. We collect every observation we can get, and here we add our domain expert insights into the loop, where we look at the data, look at different behaviors, try to identify bottlenecks, perform exploratory, then confirmatory data analysis, which is the let's look at the data and now confirm the data with statistics part of the analysis. And we try to derive some key performance indicators about our system. Now that we know this, it's like rinse and repeat. We do this after we gather enough knowledge of the system. So this is the loop that we are performing now, right around and around. But our goal doesn't stop here. After this, the road is open to use these observations and this gathered knowledge to construct a formal performance model of the system that are valid with respect to these observations we gathered. And once we have formal models, the world just opens up to us in many other fields, like we can perform automatic and cheap sensitivity analysis to different parameters. And then, for example, we can use this knowledge to automatically synthesize such network infrastructure that meets our performance requirements. Thank you. Yeah. Yeah. So now the ordering service is logically completely separate from the others, so it can be another network that doesn't execute transactions. It depends. Of course, there is a one orderer setup, which is kind of for development, but it's of course fragile in production. There is a setup where you can use Kafka and Zookeeper for crash fault tolerance. Then you can change any numbers you want for Kafka best practices. The BFT version are still under development by the Fabric team, but since this orderer only defines some simple APIs, anyone can plug in their own implementations. Yeah.
slightly different talk. Yeah, okay. So my name is Ran, and I'm a faculty at Bar-Ilan University. And as I said, it's going to be slightly a different talk. Microphone. Yes. You also want to hear me. Okay. Again, from the beginning. So my name is Ran, and I'm a faculty at Bar-Ilan University. And my talk is not about blockchain. It's about, I'm actually going to show you a coding scheme. It's about coding theory. But this coding scheme is kind of inspired by blockchain technology. And I think it's a nice use or a nice way that we can take ideas from the blockchain technology and apply them maybe to other fields. So here's the motivation, and this slide I'm not even going to talk about it, but this is the problem that we were trying to solve. So the problem is the following. You are given some function, a Boolean function, and I want you to construct a circuit out of AND gates and OR gates that actually calculate this function. But I want it to work even if some small fraction of the gates are faulty. Okay, so I want you to bring me something like this. But some of the gates are faulty, and I'm not going to define what faulty is. So this is the problem we were trying to solve. I'm not going to talk about it at all. What I am going to talk about is interactive coding. And interactive coding is the following situation. We have Alice and Bob. Alice has some input x, and Bob has its private input y, and they want to compute this function of x and y. How do they do this? Well, they need to communicate. So Alice sends a message that depends on x, M1, and Bob, once receiving M1, he computes his next message according to his y and sends it to Alice, and so on and so forth. And after maybe R rounds, their protocol yields out the output f. Okay? But now the problem is what happens when we have noise. And in this case, it's an adversarial noise. So there is an adversary that changes M2 to something else, M prime. What will happen now? What will be the output? Okay? So interactive coding, or coding for the interactive setting, is just taking this protocol that Alice and Bob had and compile it into a new noise-resilient protocol that will give us the same result, even if some of the messages were corrupted by this adversary. Okay? And now I'm going to take an assumption that will make our life easier. I'm going to assume that we have a feedback, a noiseless feedback. So both the receiver and the sender will learn MI prime, the wrong message that was received. Why am I allowed to do this? This relates to the circuits that I showed you on the first slide. Actually, if you think about it within this framework, you get this for free. So this is it's an assumption. I can use it. I get it for free. Let's just use it. And now I'm going to tell you how I am going to code any protocol to be resilient to noise using this feedback. So this is a scheme. This is the blockchain-inspired scheme. It's quite simple that I will be able to explain it to you like in one slide. So the parties kind of simulate the original protocol. They send the message that they are supposed to send. But every time they send a message, they also send a pointer to the last message that they sent and wasn't corrupted by the channel. So let's see how it works. So Alice begins with sending M1. And she sends a pointer to nothing, because this is her first message. This gets to Bob. Okay, Bob learns M1. Now he sends M2, and this is his first message. He sends it back to Alice. Now Alice sees M1, M2. She can send M3. And now she links M3 to M1, because M1 was received correctly, and M3 was received correctly. How does Alice know that Bob received it correctly? We have a feedback, right? Yeah. Because of the feedback, Alice sees what Bob receives, and she sees that he got it correctly. So this goes on, and now Bob sends M4, but there was a noise, and the noise changed the message. Now Alice gets this M4, this wrong M4. Alice doesn't know that this is wrong information. So she sends M5, but this M5 is completely wrong, because it's based on M4, which is wrong. However, Bob knows that this message was received wrong because he has a feedback. So his next message, he will send M6 and he will say, okay, I'm linking it to M2. And once Alice will get this M6, she will know that the correct information is M6 and M2, and she will know to ignore M4. Okay, so what do we have here? We have like parties constructing chains, and the output will be actually the information that is conveyed by the longest chain. Okay? So there are plenty of things I'm hiding there. Actually, they don't speak in alternating way. But if you do this, you will get a coding scheme that is resilient to an adversary that corrupts up to 1/5 of the messages of Alice, and at most 1/5 of the messages of Bob. And we show that this is the optimal thing. You can't do better than that. If I can steal 1 more minute, I will argue why it works. Okay? So what are the possible attacks? So I think about the noise as an adversary. What can the adversary do? The adversary can create his own chain. But this is the red chain. But Alice, let's assume this is Alice. Alice will never extend the wrong chain. Right? But the budget of the adversary is limited. It's limited to corrupting only 1/5 of the messages. So it cannot be that his chain is the longest. Okay? So if he starts from the beginning, that will not work. He must begin at the middle. But again, in order to work, he cannot start soon enough. He must start towards the end. But if he starts toward the end, we are able to show that all the correct information already lies here. Okay, so this like hand waving why this works. I guess this is it. Thank you very much. So currently these results are really theoretical because we are trying to figure out the limit, like the 1/5, the limit. I guess that maybe a more practical question is not to ask what is the highest limit, what is the fixed fraction, maybe the noise is very small. And then you can ask how you do it in less noise and less problem. But the practical application is rather starting the motivation. You can start the resilient circuit for small amount of noise. This actually can be done, but currently the overhead is too large. I mean, people can start systems what we can do, and this is computers, every system can do it. And some of these systems get corrupted because of manufacturing problems. Yeah. Okay, thank you.
All right, so this is technically not a student's talk, but rather a showcase of a use case of a blockchain. So, my name is Andrei. I'm an engineer at Soramitsu, and I will present a decentralized digital depository, which is a solution to store the crypto assets and exchange them. So, first I would like to show this slide. So as we see, the biggest cryptocurrency hacks and scams are the centralized exchanges. And well, since centralized exchanges are the most popular solutions to store assets right now, because we want some liquidity for the crypto assets, we really want a more secure solution for this. And well, this takes us to this problem. So the investors want a secure solution, and also since well, people are located like around the world. They are in different jurisdictions in different countries, and they want to comply to their to the jurisdiction of their country. And as I said previously, the most of the existing exchanges are centralized. And the solution is the centralized digital depository, which is a system to store the assets and exchange them on site. And it allows us to well, to use it in multiple jurisdictions because the nodes can be located in different countries and run by different parties. And the ecosystem looks like this. So we have a distributed ledger interface which connects to different blockchain networks, like for example Ethereum or Bitcoin. And the institutions that run the nodes can be located in different countries which will have different regulations. And the foundation looks like this. So the main idea is that the clients, well, they don't see all the infrastructure behind the system. They only contact the institution of their interest, for example, in their country. And so now going to the interesting part, which is how it is implemented technically. It is done by multi-signature federation of notaries. So two-way pegs were previously sort of mentioned by Maurice when he explained hash locks. And the multi-signature federation is one of other types of interledger communication, which sometimes allows us more flexible solutions since we don't need any on-chain implementations of hash locks. And so the notaries are running both networks. So it's D3, which is now well, uses Hyperledger Iroha, and Ethereum or Bitcoin or another network. So the deposits to the system are done by tokenization. So so people just deposit their assets in Ethereum, for example, to the notary wallet, and the notaries then make a corresponding transaction in D3, and withdrawals are done by multi-signature, by verifying multi-signature transactions on the target blockchain. So, for example, like multi-signature transactions on Ethereum. So, yes, that's the main part of the solution is Hyperledger Iroha, which has multi-signature transactions, and it has well, deterministic BFT consensus with finality. And another key point is that we provide the same interface as the existing exchanges, so that people can easily transfer. Well, they can get used to the new system quite easily. And what is a D3 node? So it consists of three parts. So it is Hyperledger Iroha peer, which is a part of a D3 network, then Ethereum peer or peer of another blockchain network, and a service which runs the private key generation and which listens to the transactions in both networks and generates the corresponding transactions. And how does it work for the deposits? So first, a client makes a transaction in Ethereum, for example. Then the notaries, they see this transaction, and they send the corresponding transaction to D3 network or Hyperledger Iroha here, and then all the signatures and transactions are received from the corresponding notaries, and the transaction is written to the ledger. And another good point is that all of the solution is open source, so you're welcome to contribute. So as you see, all the projects are available on GitHub, Iroha, and D3 Ledger. And that's it. Thank you.
Thanks. If you like your dad's blockchain, so much less interesting than, I won't name names, but all the other public stuff. For a few people, it is more interesting. Us. So what we are talking about is consortial, permissioned, enterprise blockchains, and in 6 minutes I don't want to get into the taxonomy. The basic idea is that there's stuff that organizations do between each other that they don't want to put on a public blockchain. So what they want to do is that they create smallish little blockchains called channels in fabric, ledgers, that connect just those organizations that are privy to some communication or other interaction, and from this you can build a network of little blockchains. So from a networking systemic perspective, what you look at specifically with Hyperledger Fabric is smallish, closed and bespoke networks from an engineering point of view. It could be otherwise, see Ripple, Corda and al, but this is what we have here. We have federated PKI based A&A, authentication and authorization, what means that you don't need proof of work, you can just sign and vote. PBFT is just that in a Byzantine way. And cryptocurrencies wouldn't even make sense, because if I do a BME currency, nobody will accept that. That lives only on our little chain. Smart contracts are called chain codes. Basically any x86 code producing language and more you can use. If you write a shim for that, this is just a little ODBC-like interface. You can write your own. Time to time I try to coerce students to write shims for interesting languages. They don't really like it. It's basically a modern rehash of distributed systems. We mostly work with Fabric. What the open questions are here right now is mostly how to engineer these bespoke networks. So less theoretical than the open questions in the public domain, but still interesting, hopefully. What one has to keep in mind is this strange form of consensus. First, you go to each organization, you have your transaction, you make them simulate its run, make them compute its hypothesized outcome, make them stamp it in a digital certificate, with a digital certificate, and when you collected all these, you put them in an envelope and go to the ordering service, which orders these into a block, and when blocks are finished, they go to the peers that may have been these endorser peers, and they process these blocks. Simple and works, question mark. What you have here is an endorsement policy. You can specify the number of organizations that have to sign your transaction in order to be acceptable. So you can go from 1 out of n to m, through m out of n to n out of n. So there are many success stories. Organizations can be connected and trade will become frictionless. Actually, what happens here is a bit of a bait and switch game, I think, because yes, you connect those organizations for first just for efficient cooperation, but what then can happen after that is that now you have a network, a consortium, and you can tell people that actually we could do reverse securitization, factoring, trade financing, insurance, reinsurance, and all the funky financial stuff on the top of those already existing networks. Some questions on our side. This is very nice, but if you come from dependability, and we do come from there, a few questions arise. What happens if I break one of those endorsing peers? It depends on my endorsement policy. If I have n out of n, breaking one peer makes the whole network unavailable. It will be secure, integrity will not be compromised, but the whole stuff will screech to a halt. That does not really happen with public blockchains. On the other hand, 1 out of n, I need only one digital signature. It will be available pretty much to up to n-1 organization failures. But security, well, you have to break or compromise only a single organization for stuff to get onto the ledger that you don't want. So you do have to analyze this, and in this context, small networks, this is pretty much an exercise in fault trees and such, and not the statistical and game theoretic stuff that we apply in public blockchains. Orderer compromises, you can do consistent reorderings and transaction drops and a few other things. And also, I advise you to check out DEFCON 26. There's a tool Tinella where they showed that this world is not really that secure as we tend to think. So, at a more conceptual level, what happens with these networks, and this is important on the incentives level, when you make away with cryptocurrencies and do networks like this, what you do essentially is that you push up the incentive structure, the incentive mechanisms, from a very technical level. We do cryptocurrencies, and this is what we do, and we have our incentives, money, up to there. You have to somehow architect a consortium of organizations that behave due to their legal agreements or what. So this is very open, and everybody seems to only wave their hands about this. This can be solved. We just have to speak about it. And there's an inversion to application gets to influence consensus now, not the other way around, as we are used to that. And if I can get just a half more minute, as engineers we are doing, I hope, interesting stuff on this ledger. This is a smart door. So 2 security guards, 1 guy that wants to enter a data center, and the door is looking at a ledger whether it can open or not. And everybody uses keycards and transactions to push the state machine forward. Now, yeah, smart contract verification is a nice thing. We have code generator for that and some Java bytecode model checking and whatnot. But what the important thing is that what you care about here is, do I get stuck inside the room with all the servers, and not whether the smart contract will terminate or cause exceptions. So when you think about verification and validation here, the goalpost goes back pretty much to embedded systems. So that's it. And if you are looking for more challenging topics, those exist here too. Zero knowledge asset transfers are coming. UTXO style tokens are coming to this platform too. But this is not the focus of what you should think about, I think, in engineering research right now. Thanks.
Hello everyone, my name is Archita Agarwal and I'm going to talk about encrypted distributed hash tables or encrypted DHTs. This is my joint work with Seni Kamara, who's also my PhD advisor. So let's first see what distributed hash tables are. They're essentially just a construct which allows us to store data on multiple machines, and these machines are connected through an overlay network. And we'll see what an overlay network is. So more formally, DHT is just a set of 3 protocols. The first protocol is a setup protocol, which takes as input the number of machines in your network, n, and it outputs an overlay network. So these red lines are representing this overlay network, and this overlay network is just a virtual network that you create on top of your actual physical network, which enables you to route things quickly in the network. Okay. And then the second protocol is a put protocol, which lets you store label value pairs in the system, and it returns nothing. So for example, assume that that node over there makes the put call. So the first thing that that node will determine is where to store that pair in the network. So let's say it determines that node has that pair has to be stored at this machine. So then this machine is called the server of the label, because it is the one who's responsible for storing that label value pair. So as the next step, okay, and generally this is done by hashing the label to determine what is the server of the label. As the next step, the request gets routed through the network until it reaches the server, at which point it is stored there. And these machines through which the request is routed are called the routers for this label. The last protocol is a GET protocol, which is just the opposite of the PUT protocol. Now, once you have stored a pair, and if you want to now retrieve the value which is associated with label, you run the GET. So GET, it follows the same thing. So the first thing the machine will do is figure out where the server is and then request it to return the value back. So I think we all are aware of its uses, and it's sort of used everywhere. Like BitTorrent uses it, content delivery networks use it, distributed file systems use it, and many a times what happens, like because blockchain has created such a big hype, that people just think that they want to use blockchains to store even the data. But most of the times they do not even need all the properties that the blockchains provide, like tamper-proof or that high degree of replication, in which case you have to go for off-the-chain solutions. And one thing is that if your data is huge, you cannot even store it on the blockchain because of the high costs associated with it, right? So at which point of time you need to go off the chain, in which case again the DHTs are used. And some examples of distributed storage systems are like these systems. So but then this is all good, and there is a lot of literature that talks about how to construct efficient DHTs. But then the question is, what if your data is extremely sensitive? So what if you want to store your medical data records, or your employee data, or your personal data, or financial data, anything? Then you don't want to just store it on the on all those machines that are in the network. So of course you encrypt the data before storing. But it turns out that design and analysis of such a DHT, which is efficient and also works on your encrypted data, is not a trivial task, because you have to figure out you have to encrypt your data in such a way that you can search on it. And second of all, you have to make sure, because you are providing that searching capability, you do not leak anything about your data. And when I say leak, you don't want to leak what your actual plain text data is, and what you are querying also should not be revealed to all those machines. So my work is actually designing these encrypted distributed hash tables. So in this work, we give a framework which takes as input a DHT and produces an encrypted DHT. So as I mentioned before, DHT is just a set of 3 protocols: setup, put, and get. eDHT is set of again 3 protocols: eSetup, ePut, and eGet. But now, instead of working on plain text data, it works on encrypted data. So I'll talk about the star over there. And we show that this framework produces provably secure eDHTs. This is a technical term in cryptography, so but I'll not go into detail, but you can prove that the eDHTs produced are sort of secure. And then we define the leakages on the routers. You remember the routers and the servers that I showed in the second slide. You define what those leakages are, which essentially means that the servers and the routers do not learn anything beyond what is defined here. And lastly, we extend our work to include in the DHTs the leaves and the joins, because the network is not static. Machines come and go. So you have to move data around as well. So we extend the work and we show how to handle the leaves and joins. So now coming to the stars, we do not handle, this framework cannot handle all the DHTs, but a subset of the DHTs, and these are the formal properties that a DHT should satisfy. But essentially, it means that the probability that a particular node is the server or a router of a label should be bounded. So if you can construct a good bound for it, then you will have low leakage. This leakages have direct effect on this. So, but most of the DHTs actually do satisfy that property, and we show it for one specific instance called. And actually, if your hashing is based on, if your DHT is based on consistent hashing, the framework would work. And as a future work, we want to see how to handle replication, because replication brings a lot of other issues along with it, because then consensus and then other more data structures are to be maintained on the nodes, which means they might be more leaky. That's it. Thank you.
Hi, my name is Vikram, and I will be talking about more speculative concurrency in Ethereum smart contracts. It sort of builds upon some of the previous work that Morris talked about yesterday, except it aims more to look at some of the actual smart contracts that already exist on the Ethereum blockchain. As Morris talked about yesterday, there's this work published in PodC that proposed execution of smart contracts just using software transactional memory. They had some simple experiments using like 3 threads, 3 or 4 different benchmarks, and they demonstrated some speed up, but as Morris acknowledged yesterday, this isn't that much of, in practice, these workloads will not be so uniform. You're not going to be running a bunch of the same smart contract per block. The question is, how would this kind of approach work on real contracts? So again, we want to execute smart contracts in parallel, but as Morris said yesterday too, we don't really have a concurrent virtual machine, so what do we do? Well, the Go Ethereum client, it provides a transaction tracer that generates these traces. And so we have to work with Ethereum bytecode instead of like Solidity or like Java if we want to work with real transactions. And basically the conflicts between these transactions can mainly come up between sload and store operations, which are just the reads and writes. So using these EVM traces, you can basically simulate and replay the traces in parallel. We use a more simplified approach than just what STM does. We just basically greedily run everything in parallel in a parallel phase, and some things abort based on read or write conflicts that we see, and then once the parallel phase ends, you start a sequential phase and just run the aborted transactions afterwards. Well, how do we measure time that it takes to execute a contract? There are 2 ways that we could do this. Either measure count the number of instructions that the transaction executed, or the amount of gas it used. Since again, we don't have a real concurrent virtual machine, so like there's no like way of time, so we have to come up with some heuristics instead. So the Ethereum blockchain is big. There are lots of blocks and transactions that have happened over since it started. So it's infeasible to analyze everything, of course. But for this work, we looked at 7 intervals during the Ethereum's existence, 1 week long each, separated by 11 weeks, and we looked at replaying some of the transactions using this technique to see how much speed up we could achieve. So these 2 plots basically summarize some of the results that we obtained. On the left, we have a plot of average speed up, where we run the simulations using 16, 32, and 64 cores. As you can see earlier on, we actually get some pretty good speed up if we even with like 16 cores. And as you expect, this will increase with more cores. But as you go from left to right, from one interval to the next, you see there's the speed up diminishes. Although we still do always have positive speed up, or more than 1x speed up, of course. The reason that you might have some slowdown is because of like transaction aborts, work that's wasted on trying to execute a transaction only to have to roll it back. And here we have like the abort rate for each of these intervals. So it starts low, and it gets pretty high, up to like 40% in the 7th interval. And I mean, that sort of explains why the speed up is much lower. So we might look at why the speed up in the 7 time interval is actually so low. So if you look at periods 5 and 6, the distribution of speed ups per block, you can see that there are a lot flatter distributions, and period 7, you have one that's much more concentrated towards the center. So I think I will skip this slide. Yeah, so I guess maybe I should have pointed this out earlier, but if you also look at the 7th time interval that we analyzed, this was during the CryptoKitties hype, where you know, the Ethereum blockchain was just clogged with all these transaction calls to CryptoKitties. So that's actually a big reason for why there was not as much speed up as you might expect, because most of the conflicts were actually from CryptoKitties, and most conflicts were actually also from other tokens. So other reasons why you might not have as much speed up as you might expect. In those previous benchmarks that Morris used, you have pretty uniform like workloads, but like in practice, you're going to be calling all kinds of transactions. You know, if your workload is pretty non-uniform, then like in the extreme case, if you have transaction that takes a lot of time to execute and a bunch of little transactions, then you're not going to get much speed up. So just one last slide. So the conclusion is, under low contention, this is a pretty effective method as long as you have low contention. And it's also worth it to maybe spend some time specifically analyzing some of the top number of contracts that cause the most conflicts. You might also consider adding more instructions to the EVM instruction set to mitigate the contention. Thanks. Yeah. Yeah. What? Yeah, then I mean, so yeah, for I guess the miners, but yeah, I guess that's a question that Morris and I actually had too. We were unsure about how much work was spent on doing like the proof of work versus like running the smart contracts, but I don't think this should be as much of an issue for validators because mostly what they're doing is just re-executing the smart contracts, and so it should at least speed up a lot of the work that the validators have to do.
All right, so my name is Daniel. I'm a PhD student with Morris, also at Brown. And I'm going to talk a little bit about, Morris sort of alluded to this, but this is sort of something that we're working on currently. Morris, I guess, formally kind of analyzed atomic, Can you hear me? Okay, cool. He formally analyzed like atomic swaps, but there are some limitations to swaps. And we're trying to generalize this to transactions. And they are transactions in the sense of a distributed database transaction, but on multiple blockchains or multiple assets across multiple blockchains is the idea. So kind of the motivating scenario, he gave kind of a variant of this scenario, but is something like this. You have these three people, Alice, Bob, and Carol. Here's Alice. Alice says, I want 1 token, and I'm willing to give like 101 ether. There's some Carol over here who says, I want 100 ether, and I'm willing to give a token. Now, they don't exactly match up, and I mean, you'll see why. And then there's some intermediate person who says, hey, I'm kind of like a market service in the middle, and people when they say they want to make trades, they report to me, and so I'll like kind of build these trades, and then I'll try to make it happen. So the role of B is to assemble a transaction and make it happen. So he says, okay, we're going to assemble this transaction where Alice gives me 101 ether, and then I take a commission of 1 ether, because why would I do this if I didn't take some commission? I need a benefit. But Carol's fine with this. She doesn't even have to, like Alice and Carol do not even have to know about each other for this to happen. And then Carol agrees to send a token to Bob, and Bob will just relay that token to Alice. So this works great, and you can imagine like if these assets were managed on a like if you imagine each of the blockchains is that manages an asset like an ERC20 token, maybe you're imagining running 2 different Ethereum networks or something like that. You can, if you trusted the participants, it's really easy to do a distributed database transaction that's solved. But the issue is that none of the participants can be trusted. So it's a variant of a distributed transaction, but it's kind of a Byzantine hardened version of a distributed transaction. So a special case of this is an asset swap. Just I want to trade some token for another token that lives on another network. Or sharding. Sharding is a special case. And also multi-step cross-chain transactions. So more generally, the idea is we want to define like a specification for an asset so that could work with this protocol. So the idea is an asset is, for our purposes, is like an ERC20 token. It kind of looks, it has a mapping from address to values. And for a given transaction that's executing across several different assets, it has a mapping that maps transaction IDs to components that correspond to a component for a given transaction. I'll talk about it in a sec. So the image you should keep in mind during this whole thing is you basically have several transactions running several components across several assets living on multiple ledgers, right? And this is like a distributed database transaction, so you want these things to execute atomically. So all the changes they make to all the ledgers should happen atomically. Either they all happen or none of the changes happen. Okay, so at first blush, it's like a distributed transaction, but you can't trust the participants now. And so you want a Byzantine hardened version of a distributed transaction. So the idea is basically you come up with use the 2-phase commit protocol from distributed transactions for databases. And you have to make it a trustless version though. And then you need this 2-phase locking, because if you have concurrent transactions trying to modify values on a given asset at the same time, you can imagine a scenario where one transaction takes money and then the other transaction thinks that address involves, still has the money, but you have to make sure you sort of implement some locking mechanism to make sure there's no conflicts like that. So for the asset, so generally when we define these assets that will work with our protocol, we say that they have to satisfy a couple criteria. The general protocol has a build phase, vote phase, and abort step, which you can do. Like this follows the two-phase commit. You can do this as an alternative to a vote, and there's a commit phase, and then an end where you complete the transaction. So the build step, following the example we talked about earlier, you have like two clients who want to do this transaction. They contact the manager. This is an analog to a distributed transaction manager in databases. He builds the transaction. So it's essentially just a series of reads and writes that they communicate. Like I want to, reads and writes that we want to make to these different assets on these different ledgers. He essentially breaks that transaction into components that live on, these assets could live on the same blockchain. It's kind of agnostic to what's happening underneath. The vote step is they basically say, okay, we saw what all the changes got submitted. It's on the public blockchain. I can audit this now. I can make sure that this is the changes that I want to make. Because, yeah, they want to make sure the manager, because no one can be trusted, they want to make sure the manager did not change some details in the transaction that they didn't send to the manager. Then there's a commit step where basically, when I describe the implementation, it's a final phase in which they can basically say like, okay, we're definitely okay with this, and then they'll finally commit the transaction. So for implementation, we need a couple of locking mechanisms. We need read locks, write locks, escrow locks, hash time locks. We've talked about, well, I'm gonna just get into the implementation real quick. So basically, the build step for this lazy version that I've implemented is the client contracts the manager and says, hey, okay, I want to make a deal. The manager says, okay, let's do a deal. He asks for hashes to build a hash time lock contract. It's a multi-secret hash time lock contract. They vote, and they create hash time lock contracts across all the assets. And then they come in and lock their assets for the duration of the transaction. The manager does it, the client does it, the other client does it. So they lock their assets so that if another transaction comes in concurrently, it cannot change. The assets are temporarily escrowed for the transaction that's executing, and another one can't come and take them. And then the commitment, they reveal the secrets to their hash time lock contracts, and the locks are released, and then someone can come in later and claim the funds for the, and it executes across all different assets. And I guess I can't get to this, but yeah, that's pretty much it.
Okay, so hi, my name is Ákos Hajdu. I'm a PhD student from Budapest, Hungary, and today I'm going to talk about the automated formal verification of Solidity smart contracts. And most of this work was actually done during an internship at SRI International, along with Dejan. So during this winter school, we've already seen that smart contracts are not that smart, and they can actually contain bugs. So let me just quickly recap you probably one of the most famous bugs, the DAO example, which I think is going to be elaborated in more detail tomorrow. But essentially, the DAO was managing balances of users in some mapping, and there was a function where the users could withdraw some amount, where we first checked that the user really has that amount in their balance, and then we transferred them this amount with this call function, and finally we decrease their balance. However, when you make this transfer, you actually pass the control flow to the receiver. So the receiver can actually call this withdraw function again, and if they call the withdraw function again, since the balance has not yet been reduced, they can transfer the money again, causing some double spending or even more. Okay, so to avoid bugs, let's do formal verification. And our main motivation was to create some method that can express a wide range of specifications, but what is also user-friendly, so we don't want Solidity developers to have a deep knowledge in formal methods. And we want it to be sound and precise, so we want to find bugs without overwhelming the developers with false alarms. And we also want this whole thing to be automated to work like a push-button method. So to address all these motivations, we created a method where the programmers can specify the expected behavior of the contracts using annotations, and then we can automatically transform the contract and these annotations into an intermediate verification language on which we can perform modular verification using SMT solvers. So in order to be user-friendly and expressive, we allow users to write specification in Solidity itself. So for example, here you can see a contract level invariant which says that the balance corresponding to the whole contract, this is an expression in Solidity, you can get the balance of the contract, is always equal to the sum of the individual user balances. And essentially a contract level invariant should always hold before and after every function, so you can treat it as both as a pre and post conditions, both as a pre and post condition. But we can also annotate functions individually with pre and post conditions. We can check for asserts, requires, loop invariants, and so on. We also have some extensions, like for example this sum function is not in Solidity, and it's also not expressible in logic, so we had to work on that. And we can also check for overflows. And in this case, what we can do is that when this reentrant call occurs, then our verifier will say that we are making this call, but the invariant doesn't hold. So because the balance of the contract has already been reduced, but the sum hasn't been reduced, we are breaking the invariant, so we report it as an error. In contrast, let's now suppose that we change the order of events. So we first reduce the balance and then we make the transfer. In this case, we are safe, and we are not reporting a false alarm, even though we are passing the control. So that's, for example, one thing that like most static analyzers or the compiler cannot detect. And as for the transformation, we use the Boogie intermediate verification language. You can see some simple example here. And essentially, the idea of our transformation is that we map state variables of the contract into global variables in Boogie. And we also have a heap-based memory model in the case where multiple contracts are involved. And we are mapping functions to procedures. And we also did different arithmetic encodings in order to have scalable bit-precise reasoning, because if you come from verification, you know that reasoning on 256-bit bit vectors is not that easy. So we did some modular arithmetic, and this was needed in order to detect overflows. And finally, we perform modular verifications, where the unit of our verifications are functions which can call each other. And essentially what we want to make sure is that if the preconditions for the function hold, and then when we execute the body, the post condition will also hold, and we can do this with SMT solvers. And just one interesting thing to remark, so I'm coming from the software verification community, and compared to that, we have some slight differences. So in this case, we're interested in the functional correctness of the contract with respect to completed transactions. So we're not really dealing with termination, because that will be ensured by the execution fees. And we're also not concerned with the expected failures. So for example, if there's an overflow, but then the user actually checks for the overflow and explicitly throws an exception, then we should not report it as an overflow, because that would be a false alarm. So yeah, thanks. That's all I wanted to say. And currently we have a paper under review, so maybe later you can see some more details on the actual implementation.